Hello everybody. Today we'll be talking about electric fields and electric field lines. So to start, what exactly is a field? A field is an invisible area that has the ability to exert a force on something. One that all of us should be pretty familiar with is a gravitational field. We'll see that in this gravitational field, there are a couple of different factors that relate to its strength. Another type of field, though, that many of us are probably also familiar with, but maybe a little bit less so, is an electric field. You can see that equation right here. You'll see that although those have different things going into them, they look very similar. An electric field is very similar to gravitational field, except in gravity, we notice that mass is an important factor, and in an electric field, we can see that charge is an important factor. We can also see that for both, distance, r, which is radius, but any type of distance, is also very important. We can see that has an inverse relationship to the strength of the field. That means that when this gets bigger, because we're dividing by it, the field strength will get smaller. One way that we like to represent electric fields is using a vector diagram. A vector is something that has a magnitude and a direction. Just like gravity, you'll notice that gravity has a direction. For us on Earth, it's always downwards. But it also has a certain amount of strength. If you were really, really far from the Earth, like in orbit somewhere, gravity would be weaker there than it is closer to the ground. Well, it's the same thing for electric fields, and so we can represent them with a vector because they have that direction and they also have strength. Now, something that makes electric fields a little bit more complicated is that we have both positive and negative charges. And so when a lot of things that were being first discovered with electricity, one of the main people that was instrumental in helping us understand electricity was Benjamin Franklin. And Benjamin Franklin, before we understood subatomic particles like protons and electrons, knew that there were two different types of charge, but we didn't really know much more than that. And so we knew that charges moved, and he decided that what would make the most sense would be for positive charges to be the charges that move. And so because of that, we have convention that current goes from positive to negative, and also that the electric field goes from positive to negative, or that the electric field line represents the direction that a positive point charge or a test charge would go. So if you took a infinitesimally small positive charge, what would it be attracted to? It would be attracted to the negative, even though that we know in reality now that most of the time negative charges, electrons, are what are actually moving, with the exception of holes that act like positive charges, or protons, or other situations where there are actually positive charges that move. This is a very important convention to remember. One way I like to remember it, because I have a background in chemistry, is the way that they represent dipoles in chemistry. So the way they represent that is by using an arrow that has a plus on the end opposite the arrowhead. And that's how you represent a partial positive and a partial negative in chemistry. And the same thing would work just to help remind you which direction the electric field goes based off of those arrows. So when we're representing the electric field as vectors, that's one useful way of representing it, because we can do vector addition. So if you have multiple charges, you have that that magnitude, which is represented by the length. So a longer field would represent, or a longer arrow would represent a stronger field. And you can, if you have multiple charges, you can add those charges. And you can see how the effects of that would go. So if you had a positive there and another positive there, you could add these arrows together to get the new vector, or the overall field as experienced by or exerted by both of these charges. There's also another really important way, and probably a more common way, that you will see an electric field represented, and that is with electric field lines instead of vectors. And so vectors, where they have this definite magnitude and direction, they have a finite length, but electric field lines are these lines that are, they originate at a charge, but they go on hypothetically to infinity. They're these endless lines that just indicate direction. It's also important to realize, of course, that these lines are just a tool that we use in physics. These aren't actual things that exist. There aren't invisible arrows anywhere, but we use them to represent charges. One of the conventions using electric field lines is that the number of arrows is used to indicate the strength of the field. And so you'd see if we make this a 2+ charge, that we might add more arrows to indicate that it's stronger. You'll notice that because there are more lines as well, the way we talk about field lines is the areas that are more dense with arrows, so ones that would have maybe more of these poking through it, would be areas that are considered to have a stronger electric field versus areas that only have one or fewer electric field lines would be areas where the electric field is less strong. Another important thing to remember would be that as we had that positive charge, the convention is still the same with arrows going from positive. So if you had a negative point charge at some point, you would draw arrows going towards that point charge. You'll also notice that another convention when drawing these field lines is that they are always perpendicular to the surface of the charge that we are representing. They never come out at an angle, but they are always coming directly out of the surface. Another important thing to recognize is that these lines are never supposed to cross. If they did, that would sort of indicate that there are multiple different electric fields at a single place at a single time, which would sort of pose this paradox. And so that's also against the convention. Instead of having them cross, what you would actually do is when you would be doing the addition, you would have them add. And that's something that you would do in vector form. That's an important rule to remember for when we're drawing multiple charges at the same time for those electric fields, that those lines never cross. You can see here, for example, with a positive charge, you have these lines going out that would eventually meet that negative charge like that. But you notice that the lines never cross. And similarly, you would notice for two positive charges, I'll give you an example of that. And again, what you would see is that you would see these lines bend away because these like charges are repelling each other. And so you would see that, again, the lines do not cross with each other. And this type of electric field line, it's really something that you use more visually, but again, mathematically, if you're going to try to find the electric field here, for example, what you would end up doing is that you would use this equation that we mentioned earlier, E equals kq over r squared, and you would just do that for both of the charges. And then you would have to remember, of course, the sign for the charges. But you would add those together or subtract them, depending on the case, in order to find the charge in this place. For example, in this case, because we use a positive point test charge as convention, this would be being repelled by this charge and repelled by this charge. And so you would find the distance between both of these charges, and you would have to, because they're in opposition, you would have to subtract them from each other. Sorry for all of those arrows. And of course, for an example with a negative charge, you would see that if we had a negative and a positive here, you did a point test charge right there, the field would look kind of like this, and the positive would be attracted here and repulsed from here. And so when you would be using that equation, you would be noticing that because they're going the same direction, that you would be adding both of the values from that together. Now earlier when we were talking about fields and how they're an area that can exert a force on an object. In this case, we're assuming that this point charge has a negligible charge, but in order to find the force that would be exerted, you would act similarly, except you use a different equation that would be kqq over r squared, and one of the charges would be due to the charge in question, another one would be the other charge. So if this charge had a non-negligible charge, say +2 coulombs, this one had +3 coulombs, you would then have to take into account that charge when trying to determine the force being exerted by these charges, remembering, of course, that these are third law pairs, and so the force experienced by this one would also be similar to the force experienced by that one, just in opposite directions. And by convention, in this case, of course, if one of the charges was negative, like this one here, negative, and that would lead to a negative force, and a negative force would imply that it is an attractive force to the particle in question, which in this case is positive. So that makes sense. Again, if you had two negative charges, then you would end up having a positive force, which would indicate a repulsive force. And that covers the basics of electric fields and electric field lines. I hope that that was informative and helpful for all of you.